Welcome to the core of symbolic AI, knowledge representation. How do we take the messy, ambiguous world of human knowledge, expressed in English, and structure it so an AI agent can actually understand and reason with it? Today, we will explore the process of translating English sentences into a formal knowledge base, or KB. We will do this by looking at two very different worlds: the abstract realm of family trees, known as the kinship domain, and the physical, rule-bound world of electronic circuits. By comparing these domains, you will learn how to build robust, logical foundations for intelligent systems. Natural language is full of context, nuance, and ambiguity. When we say Alice is Bob's mother, humans instantly infer that Alice is female, Bob is her child, and Alice is older than Bob. An AI, however, starts with a blank slate. To make English machine-readable, we must translate it into first-order logic. This process is called ontological engineering. We rigorously define the vocabulary, the objects, the properties they possess, and the relations between them. Once represented mathematically, an inference engine can deduce new, hidden facts that were never explicitly stated in the original text. Before diving into specific domains, let us review our tool of choice, first-order logic. In FOL, we use constants to represent specific objects, predicates to represent relations or properties, and variables combined with quantifiers to express general rules. The universal quantifier, for all, defines general laws across the domain. The existential quantifier, there exists, declares that something specific is out there. Through logical connectives like and, or, and implies, we can string these predicates together. An English sentence is transformed into a rigorous mathematical equation an AI can evaluate. Let us look at our first domain, kinship. This domain represents family relationships. The objects in our ontology are simply people. The relations are kinship terms: parent, child, spouse, male, female. First, we establish our basic predicates, known as axioms. For example, male-x, or parent-xi. Notice how abstract this is. We do not care about their height or eye color, only their relational links. In kinship, the vocabulary is purely relational and biological. Let us see how we translate an English definition into a logical axiom. Consider the English sentence, a mother is a female parent. How do we formalize this? We break it down. For all individuals X and Y, X is the mother of I if and only if X is female and X is the parent of I. In first-order logic, this becomes a biconditional statement. We use the universal quantifier for X and my mother X is logically equivalent to the intersection of female X and parent X. If the AI agent knows Mary is female and Mary is John's parent, it logically deduces Mary is John's mother. We can build more complex rules by chaining these axioms. Take the word grandparent. The English rule is, a grandparent is a parent of a parent. To write this logically, we must introduce a third, intermediate variable, z. For all X and Y, X is a grandparent of I if there exists some Z, such that X is the parent of Z, and is the parent of I. The AI searches its knowledge base to find a matching Z. By defining just a few primitive relations, the agent can infer the entire family tree. Now let us shift gears to a completely different environment, electronic circuits. Unlike kinship, which deals with abstract human relationships, circuits are physical systems composed of discrete interacting components. Translating this domain into logic requires a different ontological approach. Our objects are now logic gates, like and, or, and XOR gates, as well as the signals flowing through them. We also have to represent states, usually simplified to Boolean values of 1 and 0. This domain requires us to model physical connectivity and functional behavior simultaneously. To model a circuit, we cannot just say gate A is connected to gate B. Gates have specific input and output pins. Our vocabulary must reflect this rigid physical structure. We introduce the concept of terminals. We define functions like in1x to represent the first input terminal of a gate X and out1x for its output terminal. We also need a predicate to describe connections, such as connected, T1, T2, and a function to describe the signal value at a terminal, signal. We have moved from biological links to structural engineering. Let us translate the behavior of an OR gate from English to logic. The English manual says, an OR gate outputs a 1 if any of its inputs are 1. In first-order logic, we define a type predicate. Type equals OR. Then we write the rule, for all gates G, if G is an OR gate, then the signal at its output terminal is 1 if, and only if the signal at input 1 is 1 OR, the signal at input 2 is 1. This axiom perfectly captures the gate's truth table within the knowledge base. Next, we must tell the AI how the components are physically wired together. In English, we might say, the output of the AND gate connects to the first input of the OR gate. In logic, we state, connected, out 1 of gate 1 to in 1 of gate 2. But we also need a fundamental law of physics. Connected terminals share the same signal. We write a universal rule for all terminals T1 and T2. If they are connected, then signal T1 equals signal T2. By separating behavior from connections, our agent can simulate a NOI circuit. Let us compare our two domains side by side. Kinship heavily relies on binary predicates between identical types of objects, specifically people. The reasoning is largely categorical. The circuit's domain is multi-sorted. It has gates, terminals, and signal values. It relies heavily on mathematical functions mapping terminals to Boolean states. Furthermore, the circuit's domain strictly distinguishes between the structural topology, the wiring, and the functional behavior, the truth tables. Understanding these differences is crucial. The way you represent knowledge drastically changes based on the fundamental nature of the reality you are modeling. To wrap up, building a knowledge base is the art of translating the ambiguity of human language into the precision of formal logic. We saw how the kinship domain uses simple predicates to infer complex family trees, while the circuit's domain uses functions and equality to model physical wiring and Boolean behavior. Mastering this translation allows you to build AI agents that do not just guess patterns, but rigorously deduce facts, verify designs, and reason about the world with mathematical certainty.